First of all, I'm grateful to the organizers of the webinar for giving us this opportunity to present our work. And in the next 5 minutes, I'm going to talk about our proposed framework and also the software package that we developed for three-dimensional weights of evidence modeling of consular deposits using our package. And first of all, why 3D mineral perspectivity modeling? Based on this figure, as you can see in this slide, during the last 120 years, the depth of explored ore deposits have continuously increased, and the increasing shortage of easily detectable outcropping ore deposits has led more and more mineral explorers to prospect for concealed or deep-seated ore deposits, in particular for metals such as copper, which plays a crucial role in modern society. With increasing depth, traditional exploration methods are progressively becoming less efficient and more costly. Deep-seated ore deposits usually show weak exploration signals on the ground surface, and therefore there is a need to develop 2D mineral perspective mapping methods in 3D space to benefit in-depth exploration of mineral resources. The weights of evidence is a well-known data-driven and robust method in 2D mineral perspective mapping, and which is based on the Bayesian theory. And we know that the Bayesian inference approach can provide a fully quantitative and informative 3D prospective model, and it can fuse all available constraints in a probabilistically rigorous fashion. The weights of evidence represent the degree of correlation between the target mineralization and a particular model or pattern created under specific conditions known as evidence. And you have to know that the exploration criteria must include all the factors which control the target mineralization in the study area. This method estimates the posterior probability of detecting an ore body under the assumption of a conditional independence of input evidential models that at the same time it can be considered as a drawback of this method. Using the WofE method enables the user to calculate the effects of uncertainty on the weights and uncertainty due to missing information. And we have to note that implementing the weights of evidence in 3D space is much more challenging than a 2D environment. And in this slide, you can see our proposed framework for integrating the ordinary and fuzzy weights of evidence for modeling a deep-seated ore deposit in a 3D space, and we can discuss this framework later. Here in the following, I present our case study, which is a porphyry molybdenum copper deposit, copper molybdenum deposit in Iran, located within a magmatic ore subdivision called Urmiyadovta, where extensive tertiary to plioquaternary intrusive and extrusive units are exposed in a northwest-southeast trend. The major lithological units of the study area consist of volcanic and subvolcanic complexes and intrusive bodies. Volcanic rocks cover most of the study area and consist of Eocene, andesite, dacite, and rhyodacite associated with tooth breccias. The hydrothermal alteration and mineralization in our study area, Nochin porphyry copper deposit, strike northeast, southwest, and central and stock. The early hydrothermal alteration was dominantly potassic and propylitic, followed by phyllic, silica, and argillic alteration types. In general, the mineralization in our study area is the result of two geological processes, including the intrusion of the granodiorite body and the ascension of hydrothermal plates. There are 113 boreholes in our study area that provide detailed qualitative geological and quantitative geochemical data. At the first step, we split our boreholes into two subsets, the train and test subsets, and the voxel size in our modeling space is 10 by 10 by 10 meters, and the extent of our modeling space is 2 kilometers by 1 kilometer and 1 kilometer depth. And our modeling space is constrained in the upper surface to the topography, and also, it is restricted to we restricted the upper surface to using the convex hull and using the polar coordinates. And the depth of our model is also constrained to the depth of our boreholes. And In total, we have 500,000 voxels in our modeling space. And here is the actually the topography of our study area and also the boreholes we have. And in this study, actually, we use geological data that include lithology, alteration, and rock type, along with the structural data and geochemical data to create a posterior probability model. And here you can see the 3D strip logs of lithology, alteration, and rock types. And here you can see 3 cross sections from our study area. And using these 2 types of data, the boreholes and the cross section which have been built on the knowledge, our geological knowledge, and we have created these solid models of the lithology, alteration, and rock type, which have been used as input evidential layers to our modeling process. And we use closest point interpolation method to create these solid models. And in addition to these geological models, we use the structural data, and mostly based on our observations from the surface. And we created these block models from using the fault surfaces. And we also created 2 buffer zones around the fault blocks with a radius of 25 and 50 meters. And these block model of faults have been also used as the input evidential model. In addition to these evidential models, we use the geochemical data. We use the copper concentration values to train our model, and we used iron, molybdenum, and zinc as other evidential layers. And we used factor analysis to reduce the dimension of our data, and we used actually the ILR transformation to transform the data a bit prior to doing factor analysis. And we used the inverse distance interpolation method to interpolate our geochemical data. According to the cutoff grade of copper in the ore deposits located in the neighborhood of our study areas, such as Saktishman, which is a world-class ore deposit, the threshold for creating a binary model of the target ore body, which is used as the training model, is considered 0.5%. Based on this threshold, the target ore body occupies less than 3% of the total modeling space, which can be considered as the prior probability. And using the weights of evidence, we try to update this prior probability. And here is our final models. On the left side, you can see the posterior probability model, and you can see the studentized posterior probability model on the right side, which is the ratio of posterior probability to the standard deviation associated with each voxel. And we use concentration volume fractal modeling to classify our posterior and studentized posterior probability models. And in this figure, you see the 2 side views of our posterior probability model. It clearly shows that our ore body has divided into 2 parts. And we use 2 different methods to validate our results. One is prediction volume plots, which is based on the prediction area plots that was developed by Yousefi. And using these plots, we show the cumulative percentage of predicted mineralization and the corresponding cumulative occupied volume with respect to the volume against their prospectivity values. And in addition to PV plots, we compared the posterior probability and copper concentration values along the test boreholes and determined the Pearson correlation coefficient for each. Based on the results, the coefficient is above 0.5, where other boreholes surround the test boreholes at a short distance, and the boreholes located at the edge of our modeling space show a weak correlation. And now conclusions. Based on results, there is no linear relationship between contrast and fuzzy weight in continuous models, and a high concentration. High contrast does not necessarily yield a high fuzzy weight. And on the other hand, we see a clear inverse relationship between variance of contrast and studentized contrast. Based on the results, where there are a low number of boreholes, the total variance shows a high value, which gives a high uncertainty. And the contribution of uncertainty in creating the posterior probability model can lead to a higher prediction rate. The hybrid application of ordinary and fuzzy weights of evidence can be considered efficient for 3D mineral prospective modeling. And the 3D mineral prospective modeling based on the weights of evidence is highly dependent on the primary model created using the concentration values of the target element. And in future studies, we are planning to use to actually combine our method with geostatistics to improve the evaluation of uncertainty associated with our final model. We can decrease the uncertainty and increase the prediction rate in our posterior probability model by adding other exploration data such as geochemical and geophysical models, and creating more input evidential models compatible to the metallogenic model of the study area. Well, these are the references that actually the major references that we use in our study, and that reference which have been bold, which is in bold, is actually our recent paper in geochemistry. You can refer to that for more information regarding about our work, and also you can refer to our paper and software impacts for more information about our software package. And you can download our package from these two addresses, and you can also send an email to me if you face any problem in running the scripts. Thank you all for listening.